awesome.
I would laugh at you.
What?
Certainly not with you. At you.
Oh, thank you.
Well, you weren't there, so.
Well,
You weren't laughing at all.
I was at my son's soccer game. Okay. Oh. Yeah.
On church day.
I went to watch
You
you play.
allow your kids.
I went to watch you play. I went to watch you play.
Wait, no, why is that
sitting in the
Are you
field by himself?
Are you actually going to be like that as a mom? Like, are you not going to let your kids play?
Lord, was he just...
If I'm able to make it to church and they're able to.
No, my son's not in soccer. I'm totally.
I was gonna say, he would just be sitting in the
I would never let my
There's
son.
great a lot like that.
He would just be sitting in the field by himself, like...
Yeah, you'd be like.
I don't know, my poor son.
It's so cute, so I was crying. Or the part where he was going at the play, he was rolling up.
Oh, yeah.
Oh, yeah. We were like, the Pirates are about to walk on, and there's just a kid rolling in the back.
I didn't even know what was happening.
I hope that's on the video.
I was enjoying the play. Okay.
We were like, does Kramer realize those kids are just like burning face down?
I saw one dancing in the aisle.
Yeah, that's tight.
Or is he? She ran in the middle of the basketball.
Oh, they were both doing it?
Oh, yeah. Terror. I mean, they're like no, she's the worst. She either has to be held right next to you or outside.
Bryce wants to be held.
Seriously. Right next to her. If you're not holding her, right next to her or outside with her, she's crying.
Bryce, start crying.
Okay, here we go. Resistors in parallel. So series. Hey Emma, I'm talking now. When you're done, I will talk. Are you done? Yeah. Oh no! Don't do that. Don't do that.
I hate that so much.
No. Oh.
Kick him in the nuts.
Stop. Okay. You guys have got a little out of control.
It's the end of the year, guys. Do anything, guys.
How about this? How about I don't teach this lesson? You take the quiz on it tomorrow.
How about you teach a lesson and we don't have a quiz?
How about that? All right. Resistors in parallel. So in series, you have one direction that current can flow. So an example of a resistor in series is like such. A resistor in parallel is like such. So current can flow that way and current can flow that way. If this closes off, can current still flow?
Yeah. Oh, 2 or more.
I'll slow down.
Oh,
When
Oh, please have
the wire. Okay, one direction can only flow one direction here. Does that make sense? Okay. Here it can run this way and go that way, or it can continue to go and go that way and come back around and make it to the other terminal of the battery. Okay. In parallel, you have 2 or more pathways for current to flow. What's nice about it is, if one of the pathways were to somehow get opened, it would still allow current to go through the other pathways. Okay? So this is the difference between those decorative Christmas lights that were run in series, where if one of the light bulbs went out, they all went out, versus now they're starting to make, I'm assuming, them in parallel, that if one of your light bulbs goes out, the other ones still are on.
All of the lights I've used for every SLT.
If they got Willie's lights, it probably would work better.
So you're the last one to get those.
Okay? So, does that make sense? If I had, I could attach a ton more pathways to this. I just used 2 because I think that was good enough to give the example of the difference. Okay? So, that's what this says. Lights wired in parallel have more than one path for current. Okay? Parallel circuits do not require all elements to conduct. If one of them opens up, the other one, the path can still go through one of the other paths can still conduct electricity.
So it doesn't use both at once?
It does use both at once. But if this one closes off, all of them will go through this instead of, I'm not going to say half and half because it depends on what the resistors are here. Current will always take the path of least resistance.
I was going to say, so if there's a path of imagine if that was a least where
more will go through the least path,
Look at this.
and less will go through the one that has more.
Okay.
Does that make sense?
Yeah, that makes sense.
And I'm going to give you an example with later an analogy that will help you with this.
Are we ever going to figure out, like, how big
Can you
resistors
show
have to
them all around
be
the
or
other?
not?
so big that no current would flow.
You understand that?
Or like such low voltage. Not a hard
Maybe it's doable. I mean, I don't think it's as difficult as you're thinking it might be.
Wait, one pack. How many packs do you have left?
What happened? We're not doing that yet.
This is what I was thinking.
How did I get from there all the way down?
I don't know, but the next thing's supposed to say resistors in parallel at the same potential difference. No, wrong.
There you go. So, I gave you 3 equations for resistors in series. Here are your 3 equations for resistors in parallel. Your voltage is the same in parallel. Nope. Nice.
Oh.
I don't know what just happened.
If you had put plus, this whole thing would be
If you would have finished that one line.
That's the end of Grant. And then we would have had to be new building, here we come. Are we actually good at moving?
Yes, probably. I don't know what, and it just.
No, I realize sometimes I'm running total and sometimes I'm running equivalent. They're the same. You can use them interchangeably. The current will be added.
So what you're saying is the current for series?
So in series the current is the same. In parallel the voltage is the same.
Oh my word.
In series the voltage is the sum. In parallel the current is the sum. Now, if you look in you're not on your phone, muchacho, are you? Mm-hmm.
Wait, can you repeat that?
Do you care to say who you were
Kick him
texting?
in the nuts. Kick him in the nuts.
So, you should have this in your notes.
Yes.
This is a summary of series and parallel circuits, what their equations are, how, if they're the sum or if they're equal, okay? This kind of breaks down all of the equations that we're going to be using.
So you said for series, the voltage is the same, parallel to resistors.
Series, the current is the same.
Current is the same.
In parallel, the voltage is the same. And I'll give you an analogy in a little bit. Actually, why don't I just do
So
that?
like,
I'll give you the analogy right now as to how this works. Okay, so we'll go series versus parallel. Okay, we will go current. So in series, we know that the current is the what in series?
Same.
Emma.
Okay, and in parallel, we know that they add.
so I just got series is written down.
Where are you looking at?
Series is written down here. Parallel is right here.
All right, this is kind of how this would work. In series, you have one path, right? So say this is a stream of water. Okay? And in parallel, we have also a stream of water, but there are rocks in the way.
Sandwich.
The rock.
I think my lazy river analogy is working.
That's the same motion.
Okay? In series, the current through that stream is the same everywhere. One path. In parallel, we have multiple paths. And so is the current going to be the same in all 3 of these locations?
No.
No, but the sum of them will give you the total current.
That's true.
Okay? Now, the path of least resistance is going to have the most current. So technically you would say this path right here probably has the least resistance from an analogy standpoint. Does that make sense? In parallel, there's multiple paths, so that current is going to be split up down multiple paths. Now, let me explain how potential difference works. In series, your change in V total is the sum. In parallel, your V total is the same everywhere. Okay? Potential difference, think of it like potential energy of a waterfall.
Wait.
Potential difference is your potential energy stored up. Does that make sense?
But, yeah, but
It's the V total on that
Imagine
one.
I've heard 1 plus Pt2. How does it be like?
This is for parallel, that's for series.
Oh, okay.
Okay, so let's say that I have my same water analogy, and I have, I don't know, 2 rocks here. So water comes off the waterfall like this. Is the potential energy of the waterfall in all 3 of those locations different or the same? They're the same.
How much stuff is going through it though?
Depends upon the potential differences between the 2 terminals.
Okay, that makes sense.
In series, it's like this. It's like it's going, and then it drops. Then it goes, and it drops. Okay? So in series, it's like, so you have your V total, would be the difference between here and there. And this would be voltage drop 1. This would be voltage drop 2.
Why is it dropping?
What was that?
Why is it dropping?
Because the current is the same. Okay? So a way to think about this is that when you have multiple paths, your current is going to be split up, but the potential difference between the 2 terminals is the same everywhere. Okay? In this situation, you have 1 path, so the current is the same, but because you only have 1 path to go, that voltage gets shared between all of the resistors. Okay? So, that's where all of these equations kind of, a little bit of a why behind it. And believe it or not, they don't have any experimental, visual evidence of seeing this stuff. They just deduce these equations from what they see when they do experiments. Like, you can't visually see current flowing, right? But mathematically, they can see the effects of these situations. Okay? So, let's do a problem or 2.
There are no.
There are no problems?
No, next page there are. Turn the page. Next, let's turn the page.
You don't have any problems?
No.
No problem.
Go back, I bet you would.
Try it.
Really?
No, shut up.
Oh, I guess we
Shut up, Mr. Kramer.
Oh, you're investigating the quiz? This is cancer.
Okay, guess what? I'll do it right here for you. He's doing it on here. No! On my deathbed, maybe.
It's a 2 quiz.
He's probably like, that was the best Daryl impersonation I've ever done.
Oh, 1, 2. How much?
Alright, equal stop.
Okay. 1, 2, pay attention. Okay. A 9-volt battery is connected to 4 resistors, as shown on the right. On the right. Carol. Wow. Stephen, be quiet.
No, it's actually.
They're writing a paper.
Yeah. Oh, they are.
Okay, so on the right, okay. We have a 9-volt battery.
I'll see that.
And we have 4 resistors, and I gotta show you what each of those resistors are. 2, 4, 5, and 7. 2, 4, 5, and 7. And then we have to give you this information. That's why I'm giving it to you. See, on the right, don't you see it?
Will they have to give you that in parallel also?
I mean,
Or is there any way to
Well,
know
if
that
there's
parallel
multiple
stuff
paths-
is what you're saying?
there should be something that will make it obvious. Either it's in a parallel section in your homework, or it'll say it's parallel. Or they'll give you a visual.
I'm saying in a quiz.
If they give you, like in a quiz, I'll probably give you this.
Perfect.
And so you would know this is parallel how.
Well, there's
More than one path.
I was gonna say, wouldn't a series?
It has
Yeah.
like paths going this way and paths going.
So just because,
So like if this part was gone, like if this was just it, that's one path. I could have multiple resistors on that one path, but that's one path.
All the lines.
But I could go up and go this way, I can go this way, I can go this way, I can go this way.
Can you have-
Question, where do you think the current is the greatest?
at the beginning,
2,
At the
the
top.
very top.
Right here.
Which is weird because, I mean, it makes sense, but it's weird because you think the lower to the ground.
Well,
You think the lower to the
I could, just how I drew it, I could have filled it in.
Well, you think that the shorter path.
Oh,
It's always, current will always go the path of least resistance. So more current will travel through the least resistant path. Okay? This should have the least current because we know that 9 volts are going to be going through each of them.
Oh, because current's the same.
Not current, how about voltage? Sorry, I felt like an Army National Guard is
Sergeant Gonzalez.
Sergeant.
He also spelled my name wrong, so.
Sergeant Gonzalez texted you?
He texted me too. He didn't text me. Unless I haven't gotten
I
it.
He
didn't put my
said he
information.
had.
What did he
He spelled
say?
my name
He was
wrong.
like, if you ever want more information on how to be a part of the team, and you didn't say a space part, he said a part, like separate from the team. So I was like, okay.
Then I'll play Space Team. Alright.
I'll be a part.
Would you be comfortable talking on the phone at the same time?
Oh!
I
You should have said yes or the hard
Text
side.
back and say, I have a boyfriend.
I'm dating Sergeant Deuce.
All that's fun and games, but let's do this, okay?
This is even fun.
So, usually it's best, I guess it asks for equivalent resistance first. Usually it's best to find the equivalent resistance first unless they could give you the information.
Just out of the. Yes.
No.
No.
Oh,
it's 1 over.
Oh, it's dumb. It's the inverse. But it's the dumb.
Wait, why do you have 1 over 1 over?
Because,
Oh, there we go. There we go.
because the equation is this.
1 over the total equals 1.
Oh, okay, I get it.
over,
I'm just solving total. I understand
Wait,
now.
what are you solving?
But isn't
No.
So this is the equation for equivalent resistance.
I don't think.
This is the equation for equivalent resistance. So I do not want to solve for the inverse. So I brought it to the top and took the inverse.
I understand now.
So it's a double inverse essentially.
Okay.
Okay? Don't forget that. What you could do is just solve this and then 1 divided by that answer as well. Same thing. I'm just doing it all at once instead of in steps. Okay?
Wait, so it's just.
You just add 1 over R1,
Why don't you-
1 over
couldn't you just
R2,
put
1
on the
over
top like-
R3, and then do 1 divided by that.
Wait, so couldn't they just all be on the top then?
1 over X. You want to solve
You think
X?
2 plus 4 plus 5 plus 7?
Yeah.
Wait, just let him do the problem and you can see.
Okay, yeah, that makes sense. Actually, for once.
Yeah, this is a much different than 2 plus 4 plus 5 plus 7.
Yeah, you're right. That's true.
She did 2 plus 5.
Plus 9.
You
I'm gonna get a decimal on that. Okay, you guys might want to plug this in to make sure you can actually do this. I'm not sure you guys are capable enough.
Oh my
Wow.
God.
Okay, Kramer.
Kramer's actually just a jerk.
Is that in amps?
It's a great day. You make it what you want, guys.
Remember, I've never had a calculator.
He said it's so complicated. No.
That's true.
I'm sorry, but I
So now, they want to know the total current. This is total current, not current through each resistor. Because the current through each resistor will be different. So, in order to find the total current, I need to use the equivalent resistance. This is my equivalent resistance. This is my total resistance. So, to find the total current, it's going to be your voltage divided by your equivalent resistance. And it was 9 divided by 0.915.
Do you want us to plug that in because they're not sure if we can do it?
I think you do. Okay?
What happened? Hey, Crane.
9 divided by 0.915.
Oh, okay.
What'd you guys get?
Should be like
9.8 or something.
Wait, I'm gonna write my equations. For series, I'm gonna write them in the shape of an
Look
S.
at my brain now.
For parallel, I'll write them in the shape
Mr. Kramer.
Yep.
So that equation stays the same for series and
Yeah, sure. This one here?
yeah.
Yes.
Well, these are left.
But that's only when you're solving for like the equivalent like
resistance.
The principle
or
is so
equivalent.
sludge, like,
Now, it doesn't say to find the current through each of the resistor, but I'm going to
Oh,
do
that would be
that.
the same thing.
No.
Not very
That's because I made
Alpha
a
test.
If that's a test, I'd have 0 out of 1 point.
Okay, so this is the current through the whole entire thing, and the current is not the same through each resistor. We just said there's going to be more current flowing through this than through this. Let's prove it. Okay, so I of the 2 ohm resistor,
2 over,
okay, being 9 volts over 2 ohms.
Yeah, different.
Here, so.
That's 4.5.
Because you're being weird.
So 4.5s of the 9.84 amps are going through the 2 ohm resistor.
So now the thing we did on the
Now you do 9 divided by 4.
Now the I of the 4 ohm resistor, the current passing through the 4 ohm resistor would be 9 divided by 4.
So it's
so
2.25.
2.25 amps are going through the 4 ohm resistors. Now notice, this says twice the resistance, half the current.
I see.
Say that more.
Twice the resistance.
Twice the resistance, half the
it
current.
cancels more of it out.
I would have got the 100 on that test.
Partly. With extra credit.
5. 9 divided by
1.8.
That's, I
Which one, what?
was gonna
And
say.
then this answers whatever you
And now I could add all of these together, subtract it from 9.84 and find my last one.
Or you could just.
Or I could just take 9 divided by
Or
7.
you could divide that one and multiply it by
Like the square root.
that number.
That was gonna do.
Can I tell you about what happened?
The screwing?
9 divided by 7 is 1.3.
Oh.
So, now since we routed all of these, it may not give us perfectly 9.84, but it should be close when you add all those together.
Incredible, like full force.
Rounded to
Let's go
9.84.
back inside.
Okay? So just be careful.
The lights were
Listen,
off.
the key to being successful with this math, and it's not overly difficult math, but if you do not know what is constant in series and what is constant in parallel, it will make something that's really easy seem more difficult.
And this was easy test. Oh no, we made him mad.
All broke the frame of my screen.
I feel like I covered this problem more than I needed to, so it probably covers the second part of it.
Yep, so
Don't erase it.
erase it all.
I've already read, so I'm follow current.
Actually, I was thinking.
I did.
Now, if you knew, Avery, if you knew